Hello guys, this is going to be a video for lesson 17 of week 6, but I am going to start off with some review of what you took some notes on last week with lesson 14 about parabolas and just trying to get the features of a parabola based on an equation right. So we talked about this being our parent function, master function, right? When we see it this basic, it's because A is 1, B is 0, and C is 0, right? So we're going to focus a lot on this lesson about what the coefficient of x squared does to a parabola. We know if it's positive, it opens up or upward, negative opens down. Sometimes we call it concave or convex. We know if it's a fraction between, this actually should be 0, then it's wide. And if it's greater than 1, it's going to be narrow or less than -1, right? So it's in here when it's this fraction, and I guess this could be, I guess that is right with -1. Fractions are going to make it fatter, and we say that it gets compressed. And numbers that are greater than 1 or -1 are going to make it narrow, and we say that it's been stretched. Now the negative we didn't write down here, but this negative means we have a reflection and over the x-axis. So that just is a flip, if you remember. It reflects over, so it opens down now, okay? And the other thing we said, and this was just all about standard form, was that the b value would show us a horizontal translation. If you remember translation, in other words, for a slide, it doesn't change the shape of things, right? But we would know how far it was translated by this axis of symmetry, or the opposite of b over 2a. And that the c value shows us that y-intercept, and if, depending on what that is, it's moving us up or down, all based on this parent function of where, our y-intercept is 0. It's also our vertex, okay? Okay, so just a quick review of those things. We are going to be looking in a second video about how we look at those transformations in vertex form, okay? Okay, so I'm going to start, and you don't have to take these as notes, but just pay attention. We're going to talk about what A, this value of A, and what it does to our shape, because the B and C, moving it, translating it left or right or up or down, those are just slides, and it doesn't change the shape of a graph. But A does sometimes change the shape of a graph. We said it would make it narrow or wide, so that's kind of like a dilation, right? So in a master function, where y equals x squared, right, and we get this kind of a graph. Oops, let's see if I can get this to refocus for us. That's the best it's going to do, huh? No, there we go. Sorry about that. When x is 0, y is x squared, so 0 squared. And if our a value is invisible, it's this one right here. We're multiplying it by 1. So 0, right? If x is 1, y is 1 squared times our a value of 1. When x is 2, y is 2 squared times our a value of 1, right? And so on, right? And so for every horizontal distance that we move from this vertex of 0, 0, over 1, over 2, over 3 to the right, our vertical distance is going to be that squared. 1 squared, 2 squared, 3 squared. And so those perfect squares, hopefully you have those memorized, are our y distances. So over here, 1, 4, 9. And so this shape is neither narrow nor wide. This is our master or parent function from which everything gets transformed, okay? So if we do have an a value that's not 1, so for example, let's say we have an a value of 2, and that's greater than 1, so we knew that was going to be narrow. Again, we call that a stretch. So if we have y equals 2x squared, the a value is 2, we still have our y-intercept is at 0, we still have that as our vertex then, okay? No b value moving us left or right. So if that a value is 2, it's going to stretch it or make it more narrow. So think just for a minute about what that does to these a values, okay? So if y is x squared, and x is 0, 0 squared, but then we have to multiply by a, which is 2. 1, and then 1 squared times 2. When x is 2, y is 2 squared, and then we multiply by the a value of 2. When x is 3, y is 3 squared, and then we multiply it by the value of 2, right? So here are our new y values, right? And so when we graph that, we're going to see it be more narrow, right? So 0, 0. And in our last graph, right, if we think about just graphing the shape of it, okay, the shape of it was over 1, up 1 squared, over 2, up 2 squared, over 3, up 3 squared, which would be, 9, or 2 squared would be 4, right? 1 squared would be 1. So 1, 4, 9. Well, now with this stretch factor here, we're going to be increasing those. And so stretching it, making it more narrow, it's not going to go up 4 and 9. It's going to go up 2 and 8. Twice those values, right? So over 1 and up 2, twice what it did before. Over 2, 1, 2, 3, 4, and twice that, 1, 2, 3, 4. And I can't even fit the 18 on here, right? And I'm going to have the reflection over the axis of symmetry with these coordinates, right? And so this parabola is very narrow and stretched, we say, stretched upward, stretched the direction of the y-axis, okay? Now if we did the reverse of that, we would have something called a compression, where if a was a fraction, it's going to be wide, because it's going half the distance it was before. So if that a value, for example, was 1/2, so half of x squared. So we'll take our x values, square them, and then multiply them by that a factor of 1/2. So 1 squared times 1/2 is 1/2. 2 squared times 1/2 is just 2. Half of 4 is 2. Half of 3 squared, or 9, is 4.5. Okay, so we're going to have something that's wide and compressed. We're squashing it down. So again, whereas we went with our master graph, right, we went up 1, we're going to go up half of that. We went up 4, we're going to go up half of that. So, knowing that can really help us in graphing, so that we're not spending so much time trying to figure out, well, where's the next point, and doing a lot of plug and chug, right? So 2, 2 instead of 4. 2, 1, 2. When we go over 3, it's half of 3 squared. Not 9, but 1, 2, 3, 4.5. 1, 2, 3, 1, 2, 3. Okay, so this compression makes this graph a little fatter or wider. Okay, now we want to use that when we are trying to graph, because if we know based on, let's say, the vertex, if we're just taking this graph and sliding it up or down or left or right, is the shape going to stay the same? Is it just a pure translation, or is there a dilation going on? And that a value will tell me if it's compressed and those values are cut in half. The distance that we would travel on y is cut in half here. The distance that we would travel for y is doubled here. So knowing that it's typically these perfect square values when in our master parent function can help us transform any graph from there, okay? Okay, so let's just keep going. I was going to do a separate graph for this, but let's just keep going. If you need to pause and take a break, you can do that. I may have you watch another video on this very worksheet from Miss Jensen, is another high school teacher at Eagle Crest. You might know her son. At any rate, this is talking about doing transformations on our master or parent graph here and recognizing them when we see it in vertex form like this, right? And so our vertex right here is going to tell us to translate left or right or up or down. And this is going to tell us the shape of the graph, okay? So if this is our parent graph right here, where we have that distance of 1 and 1 squared and 2 and 2 squared and 3 and 3 squared. Okay. Let's just look at this one and talk about the vertex. So what is the vertex for in this format? It's just H and K, right? And we should be able to tell whether we have a maximum or a minimum based on what value? Well, the A value, right? So if A is negative, it means we have a reflection like this, and our vertex is the highest y value, so it's a maximum. When A is positive, though, it opens upward like that, and that vertex is going to be the minimum or lowest value. Okay. Now our horizontal shift is going to be left or right, and so if that's the x value, right, of the vertex here, that's H. And H, we will go left if we see x plus H. I'll talk about that in a minute. And we will go right if we see x minus H. Because if we see it in this format, which is standard for vertex form, then this number is positive. And so it would be to the right. If we see it as plus, we know it's been simplified from subtracting a negative, and that negative would be going to the left. All right, vertical shift, well, this is the y value, right, of the vertex, and that's an up or down value, right? So this is actually the K. We will go up if that is a positive, and we would move or translate down if it's negative, right? And, you know, for us, it's in either positive or it's in positive form. So if it was that we were adding a negative, they would just make it subtraction, right? Okay, now this vertical stretch factor is the one that we haven't maybe talked too much about, and this is the A value, right? A couple things to say about it. If that A value is greater than 1, then it's going to be narrow. Now, I should say greater than -1 as well, but I'm going to hold off on that until we talk about that negative thing. If it is between 0 and 1, or a fraction, we know it's going to be wide. And what I said about this before was that narrow means that it's been stretched. And we say that that A is a stretch factor. Or if it's wide, it's been compressed. I'm not going to have room for that. We'll go down here. Right, because it's been kind of pushed down if that's a fraction, right? Now the negative one I was talking about here, what happened if we had negative A over here. So a negative A value would mean that we have a reflection typically over that x-axis, okay? A is less than 0. So whether it's a fraction or a whole number, if it's negative, it's just a reflection over the x-axis. Now, keep in mind that these could be moving us, you know, up or down, and then that reflection line moves as well, okay? Okay, well, let's just do a practice on this, and again, we're going to use it as a transformation from this. So if here is a new equation, a different equation, obviously not a parent function, right? And we're looking at the vertex. So vertex, well, should be x minus H, right? And so since they've done addition, it must be that they subtracted -3 to simplify it to be addition, right? And adding a -2 would be the same as subtracting 2, right? So -2. So here's our vertex. Okay. Well, what does that tell me about how it's moved? Well, the horizontal, remember, has to do with left or right. And so because we went -3, we went left 3. And the H, or I'm sorry, the K value, that is like the y of the vertex. So it tells me if we went up or down. And since it's negative, we're going down 2. So we slide it, left 3, down 2. Does it keep the same shape? No, because of this a value being 2, we know it's going to be narrow. And because it's positive, we know it's going to open up. And so that's why we say here that it's a stretch factor. So it's going to be long and skinny, right? Okay, so based on, remember what we had before, it's not going to be like this, is it? We're going to slide it to the left 3, and then we're going to move it down 2, and then we're also going to stretch it and increase those distances from the vertex twice, okay? So put our vertex at -3, 1, 2, 3, 2. Okay. And I'm not going to go over 1 and up 1. I'm going to go over 1 and twice that distance. Reflect it. I'm not going to go over 2 and up 2 squared. I'm going to go twice that distance. Ooh, almost ran out of room there. And then I'm going to reflect it. So this graph, it's always hard for me to draw these parabolas well, but I'll give it a try. It's very narrow, right? And stretched. We'll try one more. This one I kind of modified from that worksheet and decided, well, let's make it a compression and reflect it. That's the negative part here, right? So if we look at vertex, it does have it in subtraction. So our vertex is going to be 1, and it is in addition, so that's 4. A horizontal shift would mean that we are going right 1 since it's positive. And our vertical translation is 4, and it's positive, so we're going to go up 4. Now, we don't have a stretch in this case, do we? Because this is 1/2. It's going to be wide. It's actually a compression. And because it's negative, it's going to be a reflection over the x-axis or horizontal axis. In our case, our axis, that reflection line is going to go up, okay? Okay, so if we graph this, sorry, I didn't write down what this was. It's -1/2. Again, we know it's going to be wide, and we know it's going to open down, right, because of the negative. All right, so we're going to start with the vertex because that's, the basis of what everything kind of moves around. So 1, 1, 2, 3, 4. And again, we're not going to expect it to move this typical shape, parent shape. It's going to be half of those distances, right? So instead of me coming up with an XY table, I just know instead of going over 1 and down 1, it's going to go over 1 and down 1/2. And then get reflected over here. Instead of going over 2 and down 2 squared, it's going to go half of that distance. Instead of going over 2 and up 2 squared, it's going to go half of that distance. Okay. Instead of going over 3 and up 9, it's going to go half of 9, which is 1, 2, 3, 4.5. And our reflection puts it right there. Okay. And so we see this is wider than our parent graph or master graph. It's been compressed or squashed that way, right? So you're going to use the a value to dilate the shape of it, or in a way that's either going to stretch it or compress it. And then you're going to use the vertex to translate it or slide it left, right, or up or down. Left, right based on h, up, down based on k. Okay. And then you will have to do a graph of your own and submit it or upload that to me. Okay. I'm going to attach another video that you can watch if it's useful to you. Okay.